Serum.
Sairam. So we'll start this session. So we have Marian speaking to us.
So no. Om Shri Sai Ram. A very good afternoon to everyone. I have a pleasant duty of introducing the speaker, Mr. Maraina Mayengo. He is currently serving as Assistant Lecturer in Mathematics at the College of Informatics and Virtual Education at the University of Dodoma in Tanzania. He obtained his bachelor's degree in mathematics from the University of Dodoma in 2011 and MSc in applied mathematics from the Nelson Mandela African Institution of Science and Technology, Tanzania in 2014. He is currently pursuing his PhD in the same university in applied mathematics under the mentorship of Professor Padmanabhan Shesha Iyer. Today he'll be presenting to us his research work titled Mathematical Models for the Dynamics of Health-Related Risks Associated with Alcoholism. Over to Maraina.
Namaste. Good afternoon, everyone. I would like to thank you very much for giving me the opportunity to stand before you for the next 20 minutes. Actually, I'm working under the supervision of the three professors. Professor Gosmori could not make it to be here today due to some complication in getting some visas. I'm also being supervised by Professor Padu, he was supposed to be here with us. I also have Professor Masanja from the institution. And today I'm going to present about part of my research titled Mathematical Models for the Dynamics of Health-Related Risk Associated with Alcoholism. For your information, I have just presented and defended my proposal for the last few weeks. And so this is the very much beginning of my work. And so probably, and because of time, you won't see some simulations, but I would like to present my model, the proposed model, for inputs and your comments. Before I start, it's not coming. allow me to introduce myself and my country as well. I come from Africa, the country called Tanzania. Tanzania is in the eastern part of, maybe it is not working, isn't it? Oh, that's okay now. Tanzania is in the eastern part of the continent. And this is the map of Tanzania, where I come from. And for your information, Tanzania is the home place of the tallest mountain in Africa, Mountain Kilimanjaro with its snow on top. And it is also the home of Tarangire National Park, where you can find the tree climbing lions. It's also the home of Serengeti National Park and Ngorongoro Crater, and many other attractive places you can find in Africa. You have them in Tanzania. I also, as I have been introduced, I'm doing my PhD in Nelson Mandela African Institution of Science and Technology, and this was established in 2011, and it was named after the former president of South Africa, Nelson Mandela. And so these are some pictures of our campus. And Nelson Mandela recruits only the PhD and master's students. We don't have undergraduate. So welcome. Before I start, again, I would like to start with a motivational story that how I got into this topic. About 17 years back, that was 2001, I lost my dad, the dear dad, of cancer. He got sick and died of cancer. And 10 years later, I lost my brother from what was later known to be liver cirrhosis. And the two is like cancer and liver cirrhosis are non-infectious disease. Again, after that incident again, in 3 years later, I lost another brother. That was the incident that he went for a drink out there and he got sick. And the post-mortem report said he got some contamination from the drink. So that, from that moment, that propelled my thinking about non-infectious disease, how they get into people and how can be transferred from one person to another. It was very unfortunate that when I tried to ask the medical doctors and read some reports, they said non-infectious disease cannot be transferred from one person to another, but you get it from your own course of life. And so I started reading more, and I got it from the literatures that one among the risk factors that can expose you in the risk of getting non-infectious diseases includes alcoholism behavior. And you see, when I look back, my father was drinking, not very much, but at least he was. And the other two brothers, they were drinking. I could say comparatively, they were drinking a lot. And so immediately I started thinking about the alcoholism behavior and how people get into drinking. Because if you look at the community, any community, you can group them into two, like the community of non-drinkers and the community of drinkers. When I talked to the community of drinkers, actually the main question were, how did they get into start? How did you start drinking? If you are drinking, then this is the question to you as well. And the most common answer that came out, they were like, in one way or another, they were exposed into the drinking context and then they got up the behavior. They would tell you, like, when I was a college student, my friends were drinking a lot and they took me into the where they sell beers, and then eventually I got started. But again, I started thinking about those who are not drinking. Well, you can see that is peer influence. again, I started thinking about the other group, which are non-drinkers. Non-drinkers can also be placed into two other compartments. The first compartment is those people who are not drinking just because they have never get an exposure to the drink. Or like if you ask them why they are not drinking, they will tell you like answers like, well, I never tested beer, so I don't know how it tastes, so I never got into that. But again, we have some people who are very much religious. They are connected to the faith that will inhibit them from taking the drink. And that's another group of people who are not drinking, but they have a very strong reason to take them away from the drinks. And I look at that as, you know, if you are connected to that kind of faith, then I see it is like, it's like you have been kind of vaccinated from taking the drink. If you look at alcoholism behavior as a disease. And now, we get another aspect of this, this topic, that is the influence of religious-based organization in the control or molding the drinking behavior. And so we also have some risks associated to alcoholism. I'll skip some of the slides, of course, because of the time, but these are the risks associated to alcoholism. As I said, liver cirrhosis is in the list, and it has already taken my brother. Socioeconomic risk associated with alcoholism includes the loss of life through accidents and marriage breakage. This is very common in Africa. When you, many families have gone marriage breakages because the father or the family member, maybe the father or the mother is very much engaged in the drinking. And so we also have some statistics about consumption rates of alcohol in Africa and in global and in Tanzania as well. If you look at the statistics, you see that the global per capita consumption rate is 6.2 liters per year. And in Africa, it goes up to 6 liters per year. But in Tanzania, it goes higher as much as 6.8 liters per year. And you see 6.8 liters per year is above the African rate and is above the global rate. So it is considerable high rates of alcohol intake. We also have some benefits of taking alcohol when taken moderately. You see we have some, you can see them on the slides. And there is something very interesting when I studied the alcohol consumption and the alcoholism behavior. Alcoholism behavior obeys what we call the theory of reasoned action. In my study, actually, I came to realize nobody drinks accidentally. People go into drinking because they choose to, and people don't drink because they choose to. And the the theory of reasoned action is about, like it says, any behavior, a reasoned behavior is from the intention. You can't go to the behavior if you don't choose to. And so before the intention is made up from the attitude about the behavior and the subject norms, the subjective norms. Like those who discourage drinking, it is because of the evaluation that they are doing over this part. And those who drink is because of maybe they have some positive connotation in a drinking, and maybe they want to please their friends and the companion. And so this is the flow chart of how people get the intention to the drink. And so if you are not drinking because you are religious, then probably your evaluation of the drink, it is because you see it is a sin. And then it kills the intention to get into the drink. And so the theory of reasoned action tells us that you can start somebody because of the some of his actions, the way of his life, then you can tell whether in future he will get into a certain kind of behavior or not. Because in future, you are making up your intention and later you'll get into the action. This is all about, it matches exactly with the alcoholism behavior, the way you transfer alcoholism from one person to the other. And in fact, I came to realize through this study, like, if I'm sick from cancer, I cannot transfer it to you, but I don't need to have cancer to expose you into the risk of getting cancer. Like, if I'm drinking and you're my friend and we spend most of the time around, then I can extract you into the drinking compartment, and that doesn't need me to be having cancer, to be having liver cirrhosis, to be having all those kind of non-infectious disease. But I can expose you and recruit you to all those kind of risky. So finally, I came to this model compartment. Sorry, can I use this one? It's okay. Now, you see, I have categorized the population into 6 compartments. We have a susceptible compartment, which recruits people who are not drinking, but their reasons from not taking the drink is out of religious. And we also have some religious compartment, and we have this takes the low-risk drinkers. Well, the reason is nobody starts the drink and becomes addictive at the same time. So drinking compartment or the drinking behavior is a staged process. You grow from day to day. You start by becoming maybe an occasional drinker. You drink 1 glass of wine after 2-3 weeks. And then later you become like a regular drinker. You drink regularly, and that's medium risk. And again, you can, after time, become an addictive. Like, you cannot make your life after, like, out of having the drink. And so we have, this is a recovered or the removed population. That means, well, the other experience is, if you talk to a drinker and try to say, well, you know, it is not healthy to have these drinks, then it is very, very uncommon for them to stop by just taking an advice. But if somebody is sick from any kind of disease which is connected to the drink, let's say the doctor can tell you, are you drinking? Yes. How much do you take? I take on average maybe 5 beers per week. If he tells you, okay, because of your health condition, please minimize your alcohol intake to maybe 2 beers per week, this person is going to stop completely. He has never told to stop, but he will stop completely because of the health. And so we have these people who are moving to the recovered or the removed compartment because they were told that their health is not very much supportive to continue into the drink. And so these are the interaction you see. Like, if you look at this one, religious people only remains out of the drink as much as he is faithful and loyal to the faith. But sometimes we expect some of the people to flow back to, they backslide from their faith, and then they fall into the category of susceptible. So you see the recruitment. Normally, we don't have recruitment from somebody who has never tasted alcohol and becomes alcoholic at the same point. So you can either recruit him through an occasional drinker, or maybe you can recruit him through a medium drinker, like a regular drinker. But it is very rarely to have somebody move direct from this compartment to this compartment. And so, having said that, I have the model equation. We can make 6 equations out of that interaction, and this is it. And we have some description of the parameters explained as much as they have been used. And so these are the description. And then after this presentation, then the next or the future works includes model analysis and simulations. That will take all the activities of estimating the error node as we have seen in the other presentations, and finding the stability and all those kind of stuffs. And we also going to estimate some important parameters of the model, and we have also model validation. Just like others they have said, being in India for the first time, I'm deeply appreciating each one of you for kindly hosting me here. I have just come to learn that Indian people are very kind, especially to the guest. And being the student of Professor Padu, he has made every effort for me to be here, and I would like to appreciate him. I would like also to appreciate the workshop organizing committee of the 3 universities together, and including the management of the hosting institution for reserving my place here, and thank you very much. I also have Department of Computer Science and Department of Mathematics and Computer Science, and especially the Dean or the Head of Department here with us. Thank you very much. The keynote speakers and invited speakers, all those who presented before me, and I would say they have given a very eye-opening speeches, and I like them very much. Thank you very much, and for that note, I will say thank you very much. Asante sana in Swahili. Thank you. That marks the end of my presentation, and thank you for your attention.
So, any questions you have? I think he presented just the model, not the model dynamics. So, it's our token of love.
Well, I'd like to make a comment. First of all, congratulations for the subject that you choose. It's a very interesting subject, and I think we are all of here in touch with the history of your family. I saw some in one slide that you consider, it seems, latent variables.
It seems what?
Latent variables. What I'm saying is, if one day you are interested to, for example, using a questionnaire, for example, to confirm many of the things that you said here about the behavior of the people related to the alcoholism habits. And I think maybe you can use statistical models. Statistical models, like structural equation models that I use normally in health care, for example. And I don't know if you see my talk, but is related with him. And if you are interested in the future to have data, to analyze data, okay, I will be available. Okay.
Thank you very much, Prof. And I appreciate your comment. In fact, I'll have some simulation in near presentation, future presentations, because I'm just started. I wanted to have some inputs from the model and how to make it more useful. As the saying, the popular saying we had since we started this workshop, they were saying all models are wrong, but some are useful. So the main essence of me to present here is to make it more useful than it were before. By the way, I'm taking your comment and I'll work on it. For those who could not give their comments, please, I have my email address here. You can write me and give me your comment, and I will appreciate that. Again, thank you very much for listening, and thank you very much for having me here. Yeah.
Good afternoon. Now we have two paper presentation sessions. One from Ms. Sarada Ghosh, another from Dr. Ram Singh. The paper presentation session will be for 20 minutes, 15 to 20 minutes. Please see that. There will be, try to finish by 15 minutes, and maybe you have 2 minutes questions, something like that. Okay. So first I'll invite Ms. Sarada Ghosh from IIST Shibur, a model for cancer mortality using long linear analysis techniques. It's not here.
Oh yeah, I uploaded it in the morning. So you can get from, write it on.
They are giving control. They cannot use this pointer, sir. That's the problem.
Okay. Good afternoon, everyone. Thank you very much for giving me such opportunity. Here, the model is a model for cancer mortality using log linear analysis technique. The usefulness of log linear models for contingency tables analysis is evident from its current general popularity among both statisticians and applied researchers. We have extracted US vital rates and survival data in cancer mortality from the surveillance between the year 1997 to 2006 and fit those data in log linear model. In this work, the effect of gender and different type of cancer on death rate have been demonstrated. Apart from these, the model also considered only gender effect. When beta 1 equal to 0, beta 1 is a parameter of the model. And we also considered the effect of various type of cancer, omitting the gender effect when beta 2 equal to 0. Beta 2 is also parameter. Testing and estimation for counted data are also applicable here. We have performed the goodness of fitting for each case by comparing the test statistics, deviance statistic, and Pearson goodness of fit statistics. The simulation based on R software. In the world, cancer is one of the deadliest diseases. Our body is made up of different types of cells. Generally, these cells are grown and divided under controlled conditions to create more cells, and they are needed to keep the body healthy. But in cancer cells, their uncontrolled growth of abnormal cells anywhere in a body. These abnormal cells are known as cancer cells or tumor cells, or you can say it malignant cells. These cells can infiltrate normal body tissues. Cancer refers to cells that grow out of control and invade other tissues. Cancers may be prevented by many types, just like not smoking, maintaining a healthy weight, not drinking too much alcohol. Different cancers are we can show, just like lung cancer, colon cancer. They are related to tissues. Some cancers are not related to tissues, just like leukemia. There are many treatments, just like radiation therapy, chemotherapy, immunotherapy are we can apply for treatment of cancer. The choice of therapy is based on the location and the grade of the tumor and the stage of the disease, as well as the medical state and the age of the affected people. The aim of the treatment is to complete removal of the cancer cell without damaging the rest of the body. But it is unfortunate that most of the cancer treatments have a negative effect on normal body cells. Chemotherapy is one of the treatment of cancer. It is a treatment of cancer with one or more cytotoxic anti-neoplastic drugs through some protocol. Chemotherapy also affects cells that divide rapidly under normal circumstances, cells in bone marrow, hair follicles, etc. Another therapy is radiation therapy, which involves the use of ionizing radiation in an attempt to either cure or improve symptoms. There are two types of radiation therapy. One is internal sources and another is external sources. Surgery is the primary method of treatment to cancer therapy. Surgery is most used for breast cancer generally. Immunotherapy is one of the most recent approaches for cancer. It depends on the generally accepted hypothesis. The immune system is the best tool that humans have for fighting disease. It can help the stimulating or helping the immune system to fight cancer. The approaches includes antibodies, checkpoint therapy, and adoptive cell transfer. In this work, we have fit log linear model to predict the effect of gender and different type of cancer on death rate. Some of more attractive features of this modeling system are the ease of model specification reduction, which provide the flexibility in treating both dependent and independent variables, and the fact that maximum likelihood estimate can be collectively characterized for an assortment for sampling distribution, including Poisson, multinomial, etc. As I previously told, the simulation is based on R software. Next is model derivation and preliminaries. In most studies, there are several explanatory variables which may be continuous as well as categorical. The main purpose is usually to describe their effects on responsible variables. When a model is good fitted, it evaluates the effects, includes relevant interaction, and provides smoothed estimates of response probabilities. The simplest distribution for the count data is Poisson distribution. It can take any non-negative integer value. Let y denotes the count data, y denotes the count data, and lambda equal to expectation of y. The Poisson probability mass function for y is this. The Poisson log linear model defined such as the mean of Poisson distribution is always non-negative. There was a relation between log mean and the linear predictor theta plus beta x. We can write as Poisson log linear model when x is an explanatory or independent variable. Log lambda equal to theta plus beta x. A mean satisfies an exponential relationship for this model lambda equal to exponential theta plus beta x. We can easily write this. We just take exponential function and we can write this. The model specifies how the expected counts depends on level of the categorical variables for that cell as well as association and interaction among those variables. The purpose of log linear modeling is the analysis of association and interaction patterns. When response count Ni has index equal to Ti, the rate is Ni by Ti. The expected value is lambda I by Ti. We consider as previous x is explanatory variable, so the model is log of lambda I by Ti equal to theta plus beta xi. We evaluate this log lambda I minus log Ti equal to theta I plus beta xi, and this. Log T is sometimes called offset. The mean is proportional to index with proportionally constant depending on the value of x. But when we consider the identity link, the model is such as this lambda I by Ti equal to theta plus beta xi. Here xi ti are explanatory variable, explanatory variable, and it is most important here that there is no intercept. A good fitting log linear model provides a basis for describing and making inference about association among categorical response which are in categories called categorical response. X square and G square test whether a model holds by comparing self-fitted values to observed counts. Here degrees of freedom equals the number of cell counts minus the number of model parameter. Materials and methodology. The mortality data of the cancer is provided by this site. In this work, we have considered the rates of population as per 1 crore in year between 1997 to 2006. Here, actually, we consider two types of cancer. One is colon and rectum, and second one is kidney and renal pelvis. And consider two types of gender, male and female. To use gender and different type of cancer as predictor in a model for frequency of death, the proper baseline is not the number of subjects but rather the total time that subjects were at risk. Therefore, we model the rate of death. The time at risk for a subject is their follow-up time of observation. For a given gender and different type of cancer, the total time at risk is sum of the times at risk for all subjects in the cells, those who are died. Here we consider G as dummy variable, where G1 equal to 0 for female and G2 equal to 1 for male. And C is the dummy variable for cancer type, where C1 is 0 for colon and rectum cancer and C2 equal to 1 for kidney and renal pelvis cancer. Nij denotes the number of deaths for gender GI and cancer type CJ. With its expected value lambda ij for total time risk Tij. Given Tij, the expected risk rate is this. In this work, we considered this model log lambda ij by Tij equal to this, and the corresponding model with identity link is this. Now we fit those data in this model. We fit the data for Poisson regression model considering log link, and then the corresponding model with identity link can be fit with shown in the following table, this. It is assumed that there is lack of interaction in the effects in the model. Here, model fitting uses standard iterative methods treating Nij as independent Poisson variates with mean lambda ij. This is done conditional on Tij. And last part, the concluding remarks. The methods handling order categories such as described in Feinberg, which is very useful. Here from the table we can conclude that the table, this table, beta 1 hat equal to 0.42t and the standard error is this, and beta 2 is negative and the standard error is this. It can be concluded that when the cancer type is given, the estimated rate for male is 1.54 times that for the females. That is, male are more affected in cancer, which we consider in this paper, and 95% word confidence interval is this, and the likelihood ratio confidence interval is this. This and this are very close. Goodness of fit statistics comparing Nij to fitted lambda ij or g square is this 29.59 and x square is 30.29. Here the residual degrees of freedom is equal to 1, since the 4 response counts have 3 parameters. The mild evidence of lack of fit corresponds to evidence of interaction between gender and cancer type. However, the model without different type of cancer effect, when we consider beta 1 equal to 0, that is, we consider only that type of cancers, then we get the g square is this and x square is this, and the degrees of freedom is 2. And also consider when beta 2 is 0, then g square is this and x square is this. When we consider the identity link, we get beta 1 is this, and beta 2 since we get the result beta 2 hat is negative, we omit it, and the standard error is this. And for the goodness of fitting, g square is this and x square is this. We can show that these values are very close, and here the degrees of freedom is 1. Then represent an estimated difference in death rates between the female and male gender for each type of cancer. Our goal is to control infection and thereby prevent reproductive health problems, and also aware the people about this disease. So the development of various cancer therapies and identification of most effective therapies against the spread of tumor cells should be formed as a part of future research. Okay, I acknowledge here some references. I thank UGC Grant Commission and my guide, Professor Guruprasad Samanto. Thank you so much.
Thank you, Sarada Ghosh. Any quick question, one question, just if anybody have any questions. Otherwise, we can interact with her later. Thank you once again.
Thank you so much for listening.
Now, I invite Dr. Ram Singh to present his work on Markovian epidemic queuing model with exposed, injected, and vaccination based on treatment.
Okay, it's okay. Is it working? Yeah. Good afternoon, ladies and gentlemen. First of all, I would like to thank Professor Vamsi for organizing such a wonderful workshop and inviting all of us and giving an opportunity to listen and present our work here. And after that, I feel apologetic to the audience that I could not get much time to make our PPT because Professor Vamsi is not providing us much time. He is leaving us at 7:30. So I could not get much time to PPT. Anyway, So I'm going to present here. This is my, I started on this topic, my work. This is my very basic paper. And the title is Markovian Epidemic Queuing Model with Exposed Infection and Vaccination Based on the Treatment. But before switch over to the main content, I would like to introduce the audience with some basic concept of the Markovian process. Is there any marker? So in the audience, is there any, what do you know that, what is the Markovian process? Anyhow, a Markovian process basically Markovian process is a stochastic process in which the probability of an event depends only on the present scenario rather than past state. So I'll explain to you in a very, very wonderful and very simple example. Everybody has a mobile phone in her pocket, in his or her pockets. So the call which is going to be received within few minutes does not depend upon the call which you received in the few minutes back. I mean, so that if your friend or family member is calling to you right now, that does not necessarily dependent upon the call which you have made or received few minutes back. I mean to say, your current result does not depend upon the previous state. Do you agree with me? The call which you are going to receive in right now does not depend the call which you have received few minutes back. Because your friend have talked or your family member have talked, does not depend upon. So this property is also called the memoryless property. This property is called memoryless. So stochastic process has the, this Markovian process has the memoryless property. But there is a very interesting history behind this Markovian process. The Markovian process was initiated and started by Andrew Markov. He was a Russian mathematician. So one day he was sitting in his office with his colleague, Dr. Pavels. And Pavel, there was a hard discussion between these two of the mathematicians. Dr. Pavel said that this is a necessary condition of the independence, that in order to hold the weak law of large numbers, the independence is necessary. He said no. In 1906, he presented a very interesting paper, and that paper is also available in the literature. And he told that the independence is not a necessary condition to hold the weak law of large numbers, because by providing that the outcome of the Markovian chains or process that converges to a fixed vector of the values. So this is a little bit history about the Markovian process. So after that, in these papers, we have made an attempt to investigate an epidemic MM1 queuing model with alert, infection, vaccination, and death has been considered. The main focus of this work is on the vaccination to provide the infection in a population. What is MM1 model? First M stands for your arrivals rate in a system. Second M stands for your service rate. And one is that the server. Sometimes there are already many models available in the literature. You may see that the model is M1K, M1 infinity. So these two symbols, they are for capacity of the systems. Suppose that you are working in a system, every system has a capacity. Sometimes the finite capacity and infinity stands for the infinite capacity. But we are not going to into that detail. So because our model is very simple. So in this investigations, our vaccination is a powerful tool for prevention of the disease spreading over the population size. So we have considered our population in many ways. Healthy persons become alert when they get a vaccination, and when the symptoms of the disease can be seen on them, and they may become alert, and alert may be injected due to more infection, and provision of the vaccination is provided in both alert stages, and the transition rate is followed by the exponential distribution. And the Markovian model is developed by using inflow and outflow, that is birth and death process, right, of the model. And there are transition probabilities, they are being evaluated, and after the numerical method simulation is used to validate the models. So, isn't working or? Just scroll down that, scroll down. Okay, So this is the literature survey. No need to go there. I will just come to on the model description. In the present investigation, we consider an epidemic queuing model with different states, namely empty state, healthy state, alert state, vaccination state, and infected state. We have considered the population of n size, right? And that can be affected by the epidemic. Firstly, when the sign of this epidemic we seeing in a healthy person the stage at which he is not completely infected and known as the alert state. When some symptom appears on the body, the person become alert. An alert person may change into completely infected. While the infected with this epidemic, the provision of the vaccination is also taken as a preventive tool to control on these epidemics. So there are some assumptions because no model is perfect. We have been listening from since 3 or 2 days. No model is perfect. No model is complete. No some model are insufficient. So without some assumption, we take some assumption to consideration to in the formulation of a mathematical model. So population size is taken as a n, total population, and initially the system is in empty state when there is no birth and no death, right? And from the state, make it a converse cursor. From the state, yes, the birth and the death of the person are exponentially distributed with the rate x and p, and there is small x basically. The rates by which a healthy person become alert is exponentially distributed with the rate ai, and similarly the other rates infection are also exponentially distributed with the rate a2. The rate at which alert changes into an infected is followed by the exponential distribution with the mean pi. It's a small pi. Okay, it's working. Yes. So there are some other notations for both alert and infected person. The vaccination of two types is carried out for prevention and recovery of epidemic. And there are some another notation. So we have come to the notation part where n is the total population size, right? X is the birth rate, P is the death rate, A1 is the partial infection rate, A2 is the complete infection rate, and P1 transition rate from alert state to infected state, and P2 transition rate from infection state to recovery or removal state, you can say. 0-1, the first type vaccination, basically two types of vaccination is being administered to the patient. First is a very light, you can say the mild vaccination, and other is the severe vaccination, strong vaccination. Because the persons who are at the alert stage, they may be administered to the small or mild drugs, and the persons who are fully infected, they are in the severe states, they may be administered to severe drugs, heavy dose. So 1 and 2 type of drugs has been administered to the patient, and this is another notation. It is not a 7-1 from transition alert state to healthy state, and it is pi to 2. It is basically there is notation change. The transition rate from infected state to healthy state. So let pi be the transition probability state. The system is being in the yes. Let me take you an yes transition diagram. After that, I will come back to the notation. So 0 is the basically empty state when there is no birth, no death. And there are the 6 stages are there. H stands for healthy state, A stands for alert stage, V stands for vaccination state. That vaccination is of 2 times, that is V1 and V2. And another stage is that is called the recovered stage, right? So these are some transition diagram where rates are going on. Basically, these are the transition probability states. Stochastic pass is there. Basically, there are 2 types of models, deterministic model as well as stochastic model. So why we have changed the idea of stochastic model, and why we are being motivated by this, actual reason is that when you choose the deterministic model and the deterministic model, there is no chance of probabilities there. So there is always some probabilities there. For example, if you talk of a school children or a day caring center, there is a population, finite population is there. When the disease attack that group, it doesn't necessarily that the disease is choosing directly to one person to another person at the simultaneously. It may some time, and that time can be calculated as a uncertainty times, or you can say that is the stochastic times. So that is why such type of idea has motivated me, inspired me. So why not we take this stochastic type of model in our considerations? So that was the idea basically. So these are the governing equations which we have, extremely sorry. So these equations are not seen because of some Microsoft change, I think. Yeah. So these are the some steady state equations. We have, these basically equations are called Chapman-Kolmogorov equations, right? These are the worst case process follows. So all these equations are constructed down. Next. So there are another equations. There are 7 equations in our system as per depending upon the states, our states. So these are the performance measures. In these sections, we have find various performance measures. First is the expected number of healthy persons in the epidemic system. And that can be given as EH as a X summation. Basically, instead of X, there is a summation. Instead of X, there is a summation in the verb. Summation I from 1 to N. There is we have taken the N size, N number of population in the system. So I into PHI. That is a simple basic probability expectation value. You take expectation value mean into the X into PXI. Summation, that is the simple expectation value. Expected number of alert persons in the system, that is summation I from 1 to N, i.e. PIA. Alert probabilities are there. From I from 1 to N. Expected number of infected persons in the individual system, epidemic, that is summation I from 1 to N, and I into PGI. Notation are used here. Expected number of persons under the vaccination and expected number of the persons are recovered. So these are the some performance measures which we have calculated by using our numerical techniques and solving the equations. We'll come to the numerical part. We have used the simple RK method, Range-Kutta method of 4th order. That is the best method because of its strong convergence and fast convergence and strong stability. So we prefer to use the RK method of 4th order by using the software. So these are the data wells which we have taken into consideration. This data is taken from literatures. We have not, to be honest, we have not taken any data from any center or any agency. So this is a secondary data which we have just taken from the literature to build our models. So first, in the first graphs, you have seen that the effect of, it's a theta 1 basically. Theta 1 is the basically first type of vaccination that is being administered to the alert persons. EA stands for expectation of alert person. And we have seen a very interesting trends. If you see that the value of theta as we increases, the value of theta from 0.5 to 0.5 to 0.75, the trend has been reverse. EA is going on, increases, and we decrease the value of this theta 1. Come to the second graph. Yes, another factor of also theta 1, that is on infected stage. The trend is opposite quite here. When we increase the value of theta 1, the value of EI theta is also increases. Then another, yes, it is theta 1 on ER, recovered class. So trend has been in the quite exponentially increasing orders. So this is the last graph of effect of theta 2, that is theta 2 basically, and on the ER, recovered class. And the similar trend has been seen here because of the our data available, because this all depends upon the data. Graphical result all depends on manipulation and depends upon the data. So let's come to the conclusion part. In this paper, we have simply deal with the modeling of epidemic. We use the MMI queuing model. The various concepts such as alert, infection, vaccination has been considered into a consideration because of the real life situations. And after constructing the model, transition states are formed and used system performance. And it is supposed that our investigation will be successful, maybe in the application of queuing theory. Basically, it is a part of queuing theory. In the interdisciplinary field of epidemiology, moreover, the result could be beneficial for medical practitioners and others, the person who are working in this field. So this is from my side. If you have any query, questions, curiosity to know that, you may ask.
Any questions or anything? Okay, if no questions, let again congratulate the speaker. Thank you.
Okay, so looks like we are expecting Professor Carlos, Professor Anuj and Seshar maybe by 3:30. So looks like we have little free time because we don't see the other speakers, paper presentation speakers now. So maybe we need to break. The tea should be ready any moment, maybe in 15-20 minutes time. After that again at 4 o'clock or when they come, we'll make an announcement. We'll just pass a word as soon as they come. But I'm sure photograph session is fixed at 4 o'clock. How we spend the other time depends on when they are reaching. Okay, we may have half an hour talk with Professor Carlos and other things, other gentlemen who come, right? Okay, we have to see because they are on the way. I got a message. As soon as they come, then we can see how we take for the session. Okay, they got delayed in traffic. Sairam, tea is ready. You can go to the prayer hall and have this.
you.